Hello viewers, welcome back to this channel. So in this video we are going to be handling the fifth video and electrochemistry. So this video is going to be specifically handling or addressing electrode potentials together with standard electrode potentials. So this video is presented to you by Yusuf, and don't forget to subscribe to the channel and share the video to your friends so that you can all benefit together. Like I said, this video is going to be split into two. So in this first video, we are going to be looking at electrode potentials. Now in the final video, which is going to be finalizing electrochemistry, which is going to be the sixth video, we shall be handling electrochemical cells. So this video has been made to purposely understand how electrode potential together with standard electrode potential function together with their definitions and how we can best understand them before we start on electrochemical cells, because electrochemical cells is mainly electrode potential as the backbone. So starting with the definition, we are going to define our electrode potential to be the potential difference that is going to be developed between a metal that has been placed in contact with a solution containing its ions. So take for example, if you're having a zinc rod, which is going to be the zinc metal, and then we place it in 1 molar test solution containing zinc ions. So this is what we call, so if at all this is a zinc rod and we place it in a solution containing zinc ions, the charge which is going to be created between this metal rod together with its solution containing its ions is going to be called the electrode potential. So that's why we call it the potential difference that is going to be developed between a metal that has been placed in a solution of its own ions, and the two must be in contact, because this rod that you see in this sketch is in contact with the solution that is containing its respective ions. Selected potential, you're going to denote it by capital E, and it's going to be measured with units called volts, and volts can be abbreviated or denoted as capital V. So you're going to say that by our conversion, the term electrode potential is going to mean reduction electrode potential. And how are we going to denote reduction electrode potential? We are going to look at equations specifically addressing that. So we're going to say that, therefore, in most of the work that you are going to be handling hereafter, we are going to be dealing with reduction potentials, because electrode potential is mainly reduction potentials, and you're going to be looking at how that happens. Now with this, we are going to first have an overview about the electrochemical series or electrochemical equations. So under here, we are going to say that the electrochemical series is going to be an arrangement of elements in an order which is according to their increasing electrode potentials. And you have said that reduction potentials are going to be used in the arrangement. So the one which is more electronegative has the highest electrode potential. That's how we measure electrode potential. The one which is the most negative has the highest electrode potential, because we say that electrode potentials are the same as reduction potentials. So lithium undergoes reduction to give you the lithium ion. Now, how can you identify that a specific equation is undergoing reduction? Now, the easiest way to identify a reduction equation, like I said, these ones are going to be very important in our last video, which is full of calculations. So you need to make sure that you understand them properly. For you to identify a reduction equation, you must have electrons on your left-hand side. So if you look closely across all these equations, our electrons are on the left-hand side of our equation. That means that such equations are going to be called reduction equations. Now the other way is looking at the oxidation state of the ion. For example, in the first equation, lithium is having an oxidation state of +1. But on your right hand side, after forming the product is having an oxidation state of 0. Similar applies to calcium. Calcium is having an oxidation state of +2. After reacting it with electrons, we get an oxidation state of 0. Since the atom all the elements have no charge. So we come from +2 to 0. Here in chromium, you come from +3 to 0. So here we are having a charge of +3, but up here we are having a charge of 0. So that means that we came from +3 down to 0, and that's called reduction in oxidation states. So you can either identify a reduction equation by looking at whether the electrons are on your left-hand side, or simply by looking at the oxidation states that are present on your left-hand side and that are present on your right-hand side. Now the opposite is true. For you to identify an oxidation equation, electrons must be at your right-hand side, and also oxidation states must be increasing. I hope that is clear. For reduction, oxidation states must be decreasing from left-hand side to right-hand side, but for oxidation equations, the oxidation state on an ion or an atom must be increasing. That's what we call oxidation. Or electrons must be on your right-hand side, and those ones are going to be oxidation equations. So here I give you a sample of some of the equations that you are going to be using in the next video with their sampled electrode potentials. But however, there is no need for you to cram these electrode potentials, as whenever we examine questions about it, we shall provide you with these electrode potentials. Your work will be to calculate the given number. Now, if you look at these electrode potentials properly, you can look at the absolute electrode potential of hydrogen, or the electrode potential of hydrogen, to be 0.00 volts. And this is the reason why this equation is bold. And with that reason, we are going to get standard electrode potential using the standard hydrogen electrode that you're going to look at in the next slides. But before that, you're going to first make some notes. And note number 1 is going to say that the elements that are going to have the most negative values of electrode potential are going to be highly electropositive metals. For example, some of the highly electropositive metals that you have looked at in organic chemistry, we have lithium, potassium, sodium, and magnesium. In other words, the elements that are top under the electropositivity series, which we shall look at later. But you should note that the more negative the electrode potential value is, the more electropositive is going to be that metal or the element of that metal. Now, note number 2 is that you're going to note that the elements with the more positive values of electrode potentials are going to be the most electronegative elements. In other words, most electronegative elements, that means that they are going to be the most oxidizing elements. So the more positive values of electrode potential an element is, the more oxidizing it gets. But you're going to look at that under the given examples. For example, my electronegative elements, you're going to look at bromine, chlorine together with fluorine. Now, note number 3 is that you're going to note that from the half-cell reactions, any reagent that is going to be present on your right-hand side is going to be a reducing agent, and any reagent present on the left is going to be an oxidizing agent. But you're going to make this one well detailed and explained in the next video. Note number 4 is that you're going to know that the species that are going to be present on your right for a reaction with a lower or a more negative electrode potential are going to be stronger reducing agents. So the more negative the electrode potential is for a given element, the more stronger of a reducing agent that element is. This is very, very important. You should understand this right away from the basics, because in paper 1 there are a lot of questions that ask about electrode potential specifically under this area. Also in paper 2 we bring such questions under mixed questions which require you to explain. So here, the more electronegative the electrode potential or the reduction potential of any element, the stronger the reducing capabilities for it, and you should underline that, though I forgot to bold it, than any other species with a higher or a less electronegative electrode potential. Now you're going to say that lithium is going to be the strongest reducing agent and fluoride ion is going to be the weakest reducing agent, simply because lithium is having a more negative electrode potential according to the examples that I gave you above, whereas fluoride ion is having a less negative electrode potential. Now it can either be less negative or it can be positive, but the more negative the value of electrode potential, the stronger the reducing properties of such an element, and the more positive the electrode potential, the weaker the reducing agent. But if at all something is weaker in reducing properties, that means that such a compound or an element is going to be stronger in oxidizing properties. If an element is so weak in reducing, it's going to be stronger in oxidizing properties. So you're going to say that, on the other hand, fluorine with a more positive electrode potential is going to be the strongest oxidizing agent, and lithium ion is going to be the weakest oxidizing agent. Now here, what you should take away is that the more electronegative the electrode potential gets, the more stronger of a reducing agent that element is. But the more positive the electrode potential of a particular element, the more oxidizing of an agent that element is going to be. And you're going to look at that under given examples so that we can spot the difference properly under serious and well explained examples. So looking at note number 5, we are going to say that the more positive or less negative the electrode potential, the easier it is to reduce the ions on the left hand side of your equation. So the metal on the right is going to be relatively unreactive and relatively poor reducing agent. But here we are going to elaborate this in the next video. We may not properly explain it under this video. Now looking at note number 6, we are going to say that the more negative or less positive the electrode potential, the more difficult it is to reduce the ions on the left. Like I said, that you're going to be handling this in the next video, and we shall look at the examples to bring out clearly. What you should notice that I told you if you're having electrons on your left hand side, that's going to be a reduction equation. And if you're having electrons on your right hand side, that's going to be an oxidation equation or oxidation reaction. That's what you should note. Or simply, you can look at the oxidation state. So here we came from zinc, which is having a +2 oxidation state, to the zinc metal, which is having an oxidation state of 0. That means that this is a reduction equation, because we came from +2 right away to 0. So that implies reduction. Now looking at number 7, you're going to say that the lithium electrode can as well be written as the following, but you're going to look at this arrangement and the next video. What this means simply is that lithium has been reduced from the +1 to a 0 oxidation state. That means that for us to write this expression is meaning that we have reduced the lithium ion and we have formed the lithium atoms in solution. But this one is going to be well elaborated in the next video that's going to be handling electrochemical cells together with the calculations. So here you're going to say that the process is a reduction and the electrode potential is going to be called a reduction potential. What you should notice how to identify a reduction equation and how to identify an oxidation equation, just like I previously explained. Now with that, let's look at the standard hydrogen electrode potential. Now before we look at this, like I told you, under the reduction equation of hydrogen, you saw that the reduction or the electrode potential of hydrogen was 0.0 volts. So we use the standard hydrogen electrode in determining the standard electrode potentials of other elements, simply because its cell is not going to affect the voltmeter when you are measuring the electrode potentials of other elements, simply because hydrogen has an electrode potential which approximates to 0.00 volts. So this is how a standard hydrogen electrode cell for hydrogen looks like, and you must know its gauge together with its naming because it's highly examinable, especially in paper 1 mocks. So if you look here, we're having our setup like this. So first we're having a platinum wire, but this platinum wire is going or is attached to a platinized platinum plate. So we get a platinum wire which has been attached to a plate of platinized platinum, and then we dip it in a solution of a 1 molar hydrochloric acid solution. Now the reason why we are dipping it in a solution of 1 molar hydrochloric acid solution is because I told you for us to get an electrode potential, we must get an electrode and we dip it in a solution containing the ions of what you want to get. Now the source of hydrogen is going to be hydrogen ions, and hydrogen ions can only be given by an acid. So in some books here, you may just find it has been told that 1 molar of the hydrogen ions solution, and that is also K. And we're using 1 molar because this is a standard electrode. Whenever you are dealing with standard things, we deal with unit measurements. So that's why you're seeing 1 molar hydrochloric acid solution. Now after arranging our apparatus, we get a space and then we insert hydrogen, but we insert hydrogen in this cell at standard conditions of 298 Kelvin together with 1 atmosphere. The reason why we do that is because it's a standard. If I told something is standard, that means that we need to do everything under standard conditions. The standard conditions that we're having 298 Kelvin temperature together with 1 atmosphere. Then the platinum wire which has been dipped into the platinized platinum together with the 1 molar hydrochloric acid solution. Now looking at the procedure of making this up, we are going to say that the standard hydrogen electrode is going to consist of pure hydrogen gas that is continuously bubbled over our surface of platinized platinum. And this is going to be done at standard conditions of 298 Kelvin together with an atmosphere. Then the platinized platinum that has been dipped into a 1 molar solution of hydrogen ions is going to evolve bubbles of hydrogen gas. And that's how you can describe the structure and functioning of your standard hydrogen electrode. What you need to know here is that you need to know all the naming and how the setup comes in place, because you need it to describe other experiments together with determining the standard hydrogen or the standard electrode potentials of other elements. The reason why we use standard hydrogen electrode in determining standard electrode potentials of other elements is because the electrode potential of the standard hydrogen electrode cell is approximately 0.0 volts. So that makes it convenient to be used in determining the electrode potentials of other elements. Now let's look at standard electrode potential as a topic, or we can use it in determining, or we can use the standard hydrogen electrode in determining the standard electrode potentials of other cells. But let's first look at what standard electrode potential means. So here we are going to say that when the standard hydrogen electrode is used in conjunction with the metal electrode of any other metal that has been placed in 1 molar of its ions at standard conditions, which are 298 Kelvin together with 1 atmosphere, then the EMF or the electromotive force that is going to be obtained is going to be called the standard electrode potential of that element. So by definition, we are going to define a standard electrode potential as the potential difference, or simply the reduction potential that is going to be established when a metal electrode has been dipped into a 1 molar solution of its ions. But this one must be measured relative to the standard hydrogen electrode at room temperature and 1 atmosphere. Now room temperature is the same as at standard conditions of 298 Kelvin together with 1 atmosphere. But what you should note when you are defining standard electrode potential is that you must talk about the standard hydrogen electrode, because for you to determine standard electrode potential, you must have a standard hydrogen electrode cell. So simply it's going to be the potential difference or reduction potential, because they mean the same. Potential difference and reduction potential refer to the same issues. So you can say that is the potential difference that's going to be established when a metal electrode has been dipped into 1 molar solution of its ions and then it's going to be measured using a standard hydrogen electrode at standard conditions of 298 Kelvin or 25 degrees Celsius together with 1 atmosphere. Now looking at the experimental setup is going to be according to the following. Now here is the hydrogen electrode that you have already looked at. This is the hydrogen electrode. Now with the hydrogen electrode, this hydrogen electrode gets connected to a molar concentration, of something that we are connecting it to. So this is the iron rod. The iron rod must be dipped in 1 molar concentration of its ions. So there was a mislabeling. This is not supposed to be 1 molar solution of hydrogen ions. It's supposed to be 1 molar solution of iron to sulfate. And then this side, this is an hydrogen electrode, standard hydrogen electrode. So it must be dipped in 1 molar solution of hydrogen ions or hydrochloric acid. But let's use hydrogen ions in this case. So there was a mislabeling. You make sure that you arrange that quickly. So this is a standard electrode. It is connected to a cell. We get iron and we dip it in a solution containing 1 molar solution of its ions. So iron, we can use iron to sulfate solution. So this is going to be iron to sulfate solution. This is going to be the iron rod. Now this makes a standard electrode cell by getting a metal electrode and then you dip it in a solution of 1 molar of its ions. Now what's going to give us the measurements is going to be called the potentiometer, which is going to give us the EMF. Then we use the salt bridge to allow exchange of ions from one electrochemical cell to another without actually mixing the cells. But since we are dealing with standard electrodes, all this must be happening at standard conditions of 298 Kelvin together with 1 atmosphere. So this labeling is very crucial, and this experiment is highly examined in your mock bodies. So looking at the procedure setup, you're going to say that an iron rod is dipped into a 1 molar solution of the iron to sulfate, and this is what makes an electrode cell. You must dip a metal electrode into a molar concentration of a solution containing its own ions. So we use the iron to sulfate because the iron to sulfate can easily provide us with the iron to ions. So with that, we say that the iron half cell is then connected externally by electric wires via a potentiometer to a standard hydrogen electrode, just like the way you saw in the setup. You make sure that you use your own words according to the setup. So it's connected externally using electrical wires via a potentiometer to the standard hydrogen electrode, and this potentiometer serves the function of measuring the EMF of our iron standard electrode cell. With that, we say that also the iron half cell is going to be connected internally to the standard hydrogen electrode using the salt bridge. So the salt bridge connects the two cells internally, but the potentiometer and electric wires connect the two cells externally. And the potentiometer measures the EMF of the cell, of the iron cell, but the salt bridge connects the two cells internally, and what it does is that it allows exchange of ions without actual mixing of the two solutions for actual measurements of the EMF of the other cell. Now this one is highly examined in paper 1. As we section out these two things, we ask you for the function of the potentiometer, and we also ask you for the function of the salt bridge. And we ask you for what connects the two cells internally and what connects the two cells externally. So as you have said that electrical wires connect the two cells externally, but the salt bridge connects the two cells internally. So you should be knowing that properly. And then we have said that all those ones must be done at standard conditions. Therefore, the temperature of the solution must be maintained at the standard temperature of 25 degrees Celsius, which is also the same as 298 Kelvin. So I'm going to conclude by saying that since the standard hydrogen electrode has an EMF of 0.00 volts, the reading on the voltmeter or the potentiometer is going to be the standard electrode potential of the ion electrode. Like I told you, since the standard hydrogen electrode does not give any deflection on our potentiometer or voltmeter, that means that any deflection that is observed in the voltmeter or the potentiometer is going to be specifically for the other electrode cell, which was for iron. So we shall get EMF of iron simply by the readings or the deflection that is going to be caused on our potentiometer. If you don't know how to rate potentiometer, you can also use the word voltmeter because they all do the same purpose. They all measure EMF of the cell. Now with that, you are going to make some of the following notes under the electrochemical topics or what you have already covered. So you're going to say that, remember number one, that the EMF of the cell is going to be measured without passing any current so that the composition of the chemicals in the cell remain unaltered or remain unchanged. Also, the salt bridge consists of a bent glass tube containing some of the inactive solution such as saturated potassium chloride together with a folded filter paper saturated with potassium chloride, and you see that the salt bridge connects the two cells internally simply by allowing exchange of ions in the two cells without actual mixing of the two mixtures in the standard electrode cells. So Roman number 3, you're going to say that a standard hydrogen electrode is not easy to use because it is bulky, and also it is slow to reach equilibrium together with it's highly susceptible to presence of impurities. So it is also not easy to maintain a stream of hydrogen at 1 atmosphere. So this is one of the limitations or the challenges that you may find out doing all that experiment. But however, these ones it's very rare for us to ask you such questions, because normally we just present these things to let you know about the experimental challenges that you may face in case you try to do it out practically. So electrode potentials of other metals are going to be measured in the same way. So with this, I mean that if at all you are being asked to describe an experiment to determine the standard electrode potential of any other metal other than iron, for example, it will be zinc. So what is only going to change is that you're going to be dipping the zinc electrode in a solution containing molar concentration of zinc ions, such as zinc sulfate. So with that, you'll be giving the same procedures with the same apparatus arrangement, having a potentiometer, salt bridge together with a standard hydrogen electrode. And the diffraction that is going to be caused in your voltmeter or the potentiometer is going to be the EMF of the cell or the standard electrode potential of the element that you are being examined. So it's the same procedure. Now looking at note 5, we are going to say that a porous partition may be used instead of a salt bridge. So this one may be examined, whereby we may ask you, apart from a salt bridge, which other material may we use to partition the two half cells? So here you can say a porous piece of paper or a porous material, anything like that, for as long as it's porous. That's the keyword to attain a mark under such situations. Now with that, let's talk about the factors that are going to be affecting the magnitude of our electrode potentials. So here we are going to say that when a metal electrode is being dipped or a gas is being bubbled through a solution containing its ions, it is going to undergo the following energy changes. So first is going to be converted to gaseous atoms. From gaseous atoms is going to be converted to gaseous ions, and from gaseous ions is going to be hydrated, and the energy changes that are going to be involved are going to be summarized according to the following equations. Now just like we looked at this under thermochemistry, when you place a solid metal electrode into a solution containing its ions, first it's going to be atomized, and we call that atomization energy or sublimation energy. But in electrochemistry, we are going to be using atomization energy specifically. Now, after being atomized, we convert it into ions. So gas converts into ions, and that's what we call ionization energy in inorganic chemistry. Like we looked at periodicity under that, where a gaseous atom is converted to a gaseous ion. So we call that ionization energy. And after the gaseous atoms being converted into gaseous ions, these gaseous ions then become hydrated, because we looked at hydration energy depending on the charge of the ion, or charge present on the ion, on the gaseous ion. So the higher the charge, the higher the hydration energy. So the moment the gaseous atom is converted into a gaseous ion, this gaseous ion is hydrated to form an aqueous ion, which is going to be in solution so that we can measure its standard electrode potential. So therefore, the enthalpy change associated with the following reactions are going to be as follows. So we are going to have an energy change at the end of it all, but this energy change is going to depend on all the energies. Remember that enthalpy of atomization is positive, ionization enthalpy is going to be positive, but enthalpy of hydration is going to be negative. So if our total enthalpy of hydration is greater than all these two, then we expect the enthalpy of such a solution, or such a compound, or such a solution in which these ions are present, to be exothermic. But if our total enthalpy of hydration is low, then we expect enthalpy of such a solution to be endothermic. And we looked at that in details under thermochemistry. That's why I don't want to go deeper into its explanations. So here we are going to be looking at the factors that are going to be affecting the magnitude of our electrode potentials. So first, we have said that one of them is going to be atomization energy. The metal electrode is first atomized. After being atomized into gaseous atoms, the gaseous atoms are converted into gaseous ions, and that's what we call ionization energy. We looked at this under periodicity in inorganic chemistry. And after the gaseous ions being formed, they are going to be hydrated, and the energy evolved is going to be called hydration energy. Now, the other factor that's going to determine the magnitude of our electrode potential or reduction potential is going to be the concentration of the solution in which our electrolyte has been put, or in which the electrolyte is present. So the higher the concentration, the higher the magnitude of our electrode potential, and the opposite is true. Now let's talk about each of them one by one. So let's start with atomization energy. Atomization energy is an endothermic process together with ionization energy. The only thing that is exothermic is going to be hydration energy. So the other two energies are all endothermic. And remember that I said that electrode potential, the more negative the electrode potential is, the higher it is, and the more positive or the less negative the electrode potential is, the lower it is. So you're going to say that since atomization energy is endothermic, the higher the atomization energy, the lower the electrode potential. Electrode potential becomes lower by becoming less negative or more positive, but electrode potential becomes higher by becoming more negative. So the higher the atomization energy, since it's an endothermic process, the lower the electrode potential. This is because it becomes difficult to convert an element into its constituent gaseous atoms. Then we look at ionization energy. Ionization energy requires energy, so it's an endothermic process. Being endothermic, that means that it's going to make our electrode potential less negative, or it's going to lower it. So I'm going to say that the higher the ionization energy, the lower the electrode potential, and the opposite is true. Looking at hydration energy, for an ion to be, for a gaseous ion to be hydrated, it involves release of energy. So since it's an exothermic process, that means that electrode potential is going to be becoming more negative. And therefore, you're going to conclude that the higher our hydration energy gets, the higher our electrode potential gets, or the more negative. So the more negative the electrode potential, the higher it is. And the higher the hydration energy, since it's an exothermic process, the more energy evolved, and thus the more electrode potential becomes negative. Reason being, it becomes because more energy is going to be given off when gaseous ions are completely surrounded by water molecules, which is the definition of hydration energy. Now, just like I promised, let's first look at the examples that are going to elaborate the variation of electrode potentials, one via a group together with the other. Example is going to be via a period. So we say that the more electronegative the electrode potential is, the more reducing it becomes. And the less electronegative or the highest electropositive, the weaker the reducing agent of such an element, but the more its oxidizing powers. So looking at an element, we are going to have barium with a negative 1.7, magnesium is going to have negative 2.37, calcium is going to have negative 2.87, strontium and barium, they are going to have 2.89 and 2.90 respectively. So if you look here, the more electronegative here is barium, and since it's barium, it's going to have the strongest reducing powers, and the less electronegative, which is beryllium, is going to have the highest oxidizing powers, or the weakest reducing powers. Is opposite. If something is a strong reducing agent, that means that it's a weak oxidizing agent, and if something is the weakest oxidizing agent, that means that it is the strongest reducing agent. So let's look at the questions. One is going to prompt us to give reasons, to name with reasons the strongest reducing agent. So the strongest reducing agent must be the most electronegative. And with Roman number 1, you're going to say that that's going to be barium. And whenever you're answering, avoid using symbols whenever you're answering. All elements must be given their respective names, however much the question may present them using symbols. So barium, the reason for that is because it has the most negative standard electrode potential, just like we have explained. And then the weakest reducing agent, or which can be called the strongest oxidizing agent. So the weakest reducing agent or the strong oxidizing agent must be less electronegative, or it must be more positive, and here it's going to be beryllium. Like I said, avoid using symbols, make sure that you write the word in full. And if you don't know the spelling, always refer to the periodic tables that they provide you in your laboratories. So beryllium, because it has the least negative standard electrode potential, and that's the main reason for that. Now answering part B and part C, those ones prompt you to explain electrode potential in accordance to the three energy values that we looked at. Remember that we looked at atomization energy, which is said is endothermic together with ionization energy. And we say that hydration energy is the only one which is exothermic. So if at all these two are higher than hydration energy, that means that the electrode potential is going to be less negative. But if at all hydration energy increases more than these two, that means that electrode potential is going to be more negative. Now let's look at the answering of our part B, explaining the general trend in our electrode potentials. So generally, you have seen that electrode potential becomes more negative from the first element to the last element, which is barium to barium. And the reason for that is because across a group, what happens? Ionic radius is increasing. So since ionic radius is increasing, that we start bringing the energy changes that we have been talking about. Since ionic radius is increasing, ionization energy decreases together with atomization energy. And also they all decrease. Actually, the variation of all the three energies is always following the same trend. There's no way one can be increasing and the other one is decreasing. If one is decreasing, all the others are going to be decreasing. So both ionization energy and atomization energy decrease, and also hydration energy decreases as well. But the decrease of the ionization energy together with atomization energy is going to be more rapid as compared to the decrease in hydration energy. So that means that hydration energy is going to be a bit higher or more negative as compared to ionization energy together with atomization energy, making electrode potential to be subsequently negative from one element to another. Now looking at part B, the reason why barium is having an abnormally less electronegative value, first of all, since barium is at the top of the group, we expect its ion to have the smallest ionic radius. And since its ion is having the smallest ionic radius, it has the highest charge density together with the highest polarizing power. And therefore, with that, we expect that it's going to attract many water molecules. And what did we say about attracting many water molecules in thermochemistry? The more water molecules you attract, the higher the hydration energy given off. But this hydration energy that has been given off is going to be counterbalanced with a highly positive ionization energy together with the atomization energy barium has. So you find that it's going to give an overall of a less electronegative or of a less negative standard electrode potential. It's on top of the radius, but since it has a high charge density together with the high polarizing power, its ionization energy are going to be great or high together with atomization energy. But also, its hydration energy is going to be more higher. But since everything is high, it's going to give us an overall of a less electronegative value. Now going to number 2. Number 2, we are going to look at variation of electronegativity across a period. So if you look here across a period, electronegativity becomes less negative across a period. Now here, what happens across a period? We all know that across a period, ionic radius is decreasing. What happens when ionic radius of these elements decreases? So with that, the questions are going to include the following. So Roman number 1, you're going to say the factors that affect the magnitude, which I've already talked about. You give the reason for the strongest reducing agent, which I've already given an example about. You also name the strongest oxidizing agent, and you have also looked at that. Here is going to be sodium because it has the most negative standard electrode potential. The strongest oxidizing is going to be chlorine because it has a positive standard electrode potential. Now we are going to explain the trend in the standard electrode potential of the metallic elements. And this is going to include the following. So electrode potential becomes less negative from sodium to aluminium. I said that make sure that you don't use symbols as you are explaining the trends or as you are explaining anything in chemistry. Make sure that you write symbols using their names. Majority of you lose out marks because of that. So you have seen that those elements, the ionic radius is going to be decreasing, and therefore ionization energy is going to increase, or the energy are going to increase. So ionization energy increases, atomization energy increases together with hydration energy. However, the increase in both atomization energy and ionization energy are going to be more steeper or more rapid than the increase in hydration energy. So with that, you'll find that the electrode potential is going to become progressively less negative from one element to the next. So with that, this brings us to the end of this video, which was about electrode potential specifically. You dive into your question banks and you try to look for more numbers that are related to this video, and make sure that you test out yourself and address your concerns to the WhatsApp group in case you find any. So this video has been compiled and revised by Yusuf. You are advised to like the video, share the video to your friends, and make sure that you leave a comment about the presentation of this video for improved services. So we meet in the next video that's going to be encompassing electrochemical cells together with their calculations.